our next topic is a really neat feature of Python. We're going to use it to create iterators that allow easy access to internal data structures of a class. But generators are far more general. They can be used to implement coroutines. And in fact, if we have to build a factory that produces a sequence of values, sometimes it's much easier to generate each value on demand rather than try to generate them all up front. And that's what generators let you do. I hope you have fun with the finger exercise at the end of the next video segment. I thought it was pretty neat to build a little factory that generated an infinite sequence of prime numbers. Let's look at one of the features of Python, which may help with some of the inefficiencies caused by data hiding in our class objects. Any procedure or method with a yield statement is called a generator. So it looks just like a procedure, but as a procedure whose body contains one or more yield statements, Python says, aha, that procedure or method, if this was inside a class definition, is a generator. When I call such a procedure, instead of getting back a value, I get back a generator object. And then I can use that generator object as follows. I can call its next method. And the next method basically executes the procedure, and let's see what happens. So when I actually call the next method of the genTest generator object, this one that got returned when I call genTest, the first call to next will start execution of the procedure in the first line of the body of the genTest generator. And the first thing I see is a yield 1. So at that point, execution will be halted, and the value that was in the body of the yield statement is returned as the value of that call to the next method. The next time I call the next method, execution resumes at this point, and we keep executing more statements in the body until we run across either another yield, in which case we do the same thing, suspend execution, so forth and so on, or we run off the end of the procedure. And when that happens, the generator raises a particular Python exception called stop iteration. That seems a little complicated, but let's watch it in action. So here we go. We have our little generator definition over here in our editor window. Let's go off and make one. So we're going to go off and say, call that genTest generator, and you can see what we get back as the generator object. Now I can go off and start calling the next method on the generator object. The first time I call it, execution begins, and with the first statement I run across as a yield statement. So at this point, execution will be suspended after the yield statement, and the value that gets returned is 1. If we go off and continue to call next, we get back the value 2, and a third call to next will run off the end of the procedure, and you can see indeed we do get a stop iteration exception. Now that might seem a little cumbersome, but fortunately 4 knows all about generators. So I'm going to go off and create a newly initialized generator, and it's going to be the thing I'm going to iterate over. So the for loop knows that to do successive iterations over a generator, he keeps calling next until it gets a stop iteration exception, at which point the for loop finishes. So in this case, I'm just going to print out all the values that get returned by the generator that was returned from my call to genTest. And you can see the for loop works great. This is sort of fun. Let's imagine a slightly more complicated generator. Here's a generator that will produce successfully for each call to next all the numbers in the Fibonacci sequence. So if we're going to go off and do that, so here I'm going to say my Fibonacci generator. It's like so, and indeed fib is another generator, so I can say fib.next. Well, I got the first value back, so let's see how the Fibonacci generator is working. So I have a little bit of state inside the generator, some local variables to sort of remember where I am in the sequence. To generate Fibonacci, you can see the formula for Fibonacci here. I need to know the last 2 elements of the sequence. So I initialize the last 2 elements such that the first call returns the first number in the Fibonacci sequence, which is 1. And then each successive iteration, where I'm now I keep executing till I get down to here, I then yield the next value in the sequence. I update my internal memory to remember the last 2 values, and then I suspend execution at that point. When I return, I'm going to update my little memory about what the last 2 values are and iterate through the loop. So each time through the loop, I'm generating a next element of the Fibonacci sequence, and then stopping execution. And when I resume execution, I finish off the loop by updating where I am in the sequence and then going on and generating the next element. So if I go off and call fib.next, ooh, so far so good. 1, 2, 3, whoops, can't type. Fib.next, great. So we expect now the next element should be 3 plus 2, which is 5. So far so good. And in fact, I can go off and ask for all. I'm going to just start with a fresh Fibonacci sequence now. I'm going to go off and ask for all the objects in all the numbers that get generated by my Fibonacci sequence generator, and I'm going to print them out. Interestingly, you can see this will basically run forever. It's an infinite sequence. Because of the while loop, it never returns. And you can see the Fibonacci numbers are slowly getting bigger and bigger and bigger as we go on. Cute. I've stopped it with an execution, Control C on the keyboard. So you can see generators are a useful way of sort of going through a sequence of values without actually generating all the values in advance. How does that help with the problem we started off with? In other words, we'd like to make some of our data hiding a little bit more efficient. So before, when we asked for a list of all the students, we actually made a copy of that list. If all we're going to do is support iterating through that list, sort of asking for each element of the list in turn, we can replace this rather inefficient list copying operation instead with a for loop that yields the result, yields the students one by one. So now all students, instead of returning a list, returns a generator, which we can also use inside of a for statement, as we just saw. And each time the for loop asks for the next student in the list, what I get instead is the sort of where we are in the list is now being remembered by the generator, and it just sort of yields the students one by one by one. And eventually, after I get to the last student of the list and this for loop completes, the generator then will tell the for loop to stop iterating. So this is a much cleaner way of sort of allowing people to run operations on the list of students in the class without actually going through the expense of returning them the list itself.